I'm Paul Ferguson. This is Nathan McConnell, Devin Rydell, Wilson Miner. We decided to design a Folgers Coffee satellite. Here at Folgers Coffee, since we've been around for nearly a century, I feel like the next step is to take our product to space. Through space, we can spread our liquid goodness into the atmosphere for everyone to enjoy. The basic summary for our satellite is that we utilize nuclear power. We decided upon this due to its long-term capacity and its large electric output. We also account for incident radiation on the satellite based on the many celestial bodies that we'll encounter, such as the Earth, the Moon, and the Sun. Radiators were used to reject excess heat coming off of the incident radiation and also from the micronuclear reactor. A pump was used along with the reactor to push ammonia through a loop to cool the electronics in the reactor core. To show an overall diagram of the locations of these parts in the satellite, we have the radiators located on the outside portion of the core, where radiation panels are hooked up to these radiators to correctly shield them from the incident radiation. We also have the reactor on the outside of the core that will be hooked up to the ammonia system that will be cooling off the radiators, electronics, and the core. All these are located on the outside to make it easier on calculations to make sure we can make certain assumptions. For our overall flow, we start with the electronics, then go to the reactor, the radiators, the pump, and then we repeat the cycle. For this cycle, we assumed it all to be within steady state, for there to be no pressure drops. The core is also cooled through the copper piping and the ammonia system connected to the radiators. Within this entire system, the highest ammonia temperature is at 151.5 degrees Celsius. Meanwhile, the lowest ammonia temperature is at 10 degrees Celsius. These are the extreme moments within the loop for the ammonia.
Now I'll be talking about the incident radiation from the celestial bodies and our accommodations for them. We'll begin with the body assumptions. The Earth is the only one that is not modeled as a point source. So we had to have a view factor for that one that's not one. But the Moon and the Sun are modeled as a point source. So we can assume that they are one. From chapter 13 and 12, over solar radiation, we got our solar constant, and then we modified that as we went. Our radiators and body are opaque and gray, and radiation from space is neglected as it is very small. Our satellite is in a cislunar orbit at about 250 miles above the Earth. It is exposed to the sun for 12 hours a day and makes a full orbit around the Earth every 90 minutes. So it's exposed to the sun for 12 hours a day. It's dark for 12 hours a day. And the highest temperature is 120 degrees Celsius, and our lowest temperature is negative 160 degrees Celsius. So, like I said, the Earth and the Moon, or the Sun and the Moon, are point sources, and the Earth is not. Considering this, our worst case scenarios were the Sun, the Moon, and the Earth all shining on the satellite, and then just the Earth during nighttime shining on the satellite. For those, the Earth and the Moon and the Sun were point sources once again, and the Earth was not. The calculation for the Earth's U factor is down at the bottom there. For the radiation on the satellite, they were calculated in mass, the 4 different ones. So for our hottest worst case scenario, the radiation from the sun is at 1,300 watts per meter squared. The radiation from the moon is at about 6 watts per meter squared. And the radiation from the Earth is at 400 about watts per meter squared. And then at nighttime, the radiation from the Earth is at about 360 watts per meter squared. This is assuming that the Earth is at an approximate 20 degrees Celsius during the day and about 10 degrees during the nighttime. The radiator sizing was kept constant, and we changed the amount of radiators depending on how much heat we needed to experience.
Now we'll talk about the electronics and how we modeled that. The electronics generate 5.5 kilowatts of heat at the core of the satellite. Nuclear power was chosen to power the electronics as well as the pumps. The electronics need to be kept at 30 degrees Celsius, and the satellite needs to be kept anywhere from -10 to 40 degrees Celsius. So to cool the electronics, we model it as external flow over a flat plate and it being made out of a copper heatsink. Our heat transfer coefficient for that was 56.53 watts per meter squared Kelvin. And the temperature out was 303 Kelvin. Now we'll go over our power generation and the reactor we used. We got a micro reactor from Illinois National Laboratories and their MARVEL team, that stands for Micro Reactor Application Research Validation and Evaluation Team. That'll power our pump and our electronics, and we use copper pipes and ammonia fluid to cool the reactor and heat going into space. The reactor parameters are generates 85,000 watts of heat and 10,000 watts of power. To model the pump, we assume no pressure drop, and the amount of work that the pump is using to be 4 times the amount of work required to get the fluid from 0 to operating velocity. Our operation velocity is 22.36 meters per second, and that is based off the hottest case scenario with sun, moon, and earth are shining on the satellite.
So now that we have all this power, which inherently comes with quite a bit of heat, we need a way to get rid of all this heat. And that's where the radiators come in. So this is our radiator diagram. We chose the material for our radiators to be titanium. And we chose this material due to its efficient cooling and strong high temperature performance. The radiators in the diagram show that they're placed around the core, and they keep it at the needed -10 degrees Celsius to 40 degrees Celsius, as specified. And we are also using, like mentioned previously, that we're using ammonia, and this will allow us to stabilize the core to 30 degrees Celsius. For the radiator modeling, for most of these calculations, we have the incident radiation from the worst case scenario to be about 350 watts per meter squared. And this means that because the radiators are pretty much in space and a black body, they can passively reject 18,900 watts. And this means that there is 61,100 watts remaining for the closed-loop system to reject. And we also chose to coat our radiator panels in a white paint. This will help reflect the sunlight that hits them. And a lot of our modeling for the radiator was based on the ISS system, which is the Active Thermal Control System. On the diagram on the right, you can see that there is the ISS, what we have done, and they're cooling solar panels as well as the radiators at the same time, but because we're only doing nuclear power, we also use ammonia, which we also took from them, and we're inspired from their overall design. So continuing on the radiator modeling, we designed them to reject 85 kilowatts. We covered them in white paint due to the high emissidity of white paint and also the low absorption of white paint. We modeled it as diffuse and opaque. We used equation 12.6 from the textbook. And then we arranged this equation to calculate the total area required. And then we came up with 3 meter by 3 meter panels for the radiators, which we totaled up to be requiring 6 of those. And then we back solved for the surface temperature, which resulted to be 424.62 Kelvin. The heat transfer coefficient found was 41.56 watts per meter squared Kelvin based on the Chernobyl oil. And then shown below are equations from chapter 12, and we use the energy balance to make sure that everything worked out correctly. On the bottom right, you can see table 12.2, which is where we got the values for the white paints, the emissivity and absorption. Continuing on with material reasoning, as mentioned previously, white paint was chosen for the radiators. It has high reflectivity, low weight properties as well. And we also chose titanium due to the high temperatures of the nuclear reactor. Aluminum is actually a better thermal conductor than titanium, but due to the high temperatures of our system and using nuclear power, we thought for a good factor of safety, we would use titanium instead, which is also commonly used in industry. On the table on the right, this is table A.1 from the appendix. This is where we got all of our material properties for the copper, pure copper heatsink, as well as the titanium and other comparison material properties.
In conclusion, with Folgers Coffee and the satellite design, we're able to spread all of this coffee into the atmosphere where no one will be able to sleep ever again. It'll be a golden age for humanity. Thank you.